started? All right, so remember last time, in our online meeting, last time we started talking about sequential circuit analysis. So once you're given a circuit that has got flip-flops on it, I actually walked through the procedure of analyzing a sequential circuit, which may or may not do something useful. And I have got also an in-class exercise, if you recall, right? There was 2 JK flip-flops. The example that I walked through was based on a D flip-flop, 2 D flip-flops. So let me just start with that, just remind you what we talked about. Then I'm going to jump onto that in-class exercise, okay? Which I want to go through, probably to raise some questions. Maybe you couldn't ask in our online meeting, but you will be able to ask today. Okay, so in any type of sequential circuit, you will have multiple flip-flops, all right? To do something useful, you need multiple flip-flops to create different states, all right? So in that example with the D flip-flop, we got 2 D flip-flops, okay? This is D, D. There's only one input, as you can see, and this is my clock signal, all right? This is my clock, all right, clock. And you have Q, Q prime, right, and Q, Q prime, okay? And of course, this is your sequential part. This is your memory section of your circuit. Let's think about this as being, so maybe I can use another color to show you that this is, okay, is your sequential part. Sequential part of the circuit. In other words, this is where the memory is used, all right? And on top of that, you can have a combinational circuit here, okay, which will use inputs as well as the current state, which the current state will be taken from the outputs of these flip-flops, all right? So, for instance, the input of this flip-flop is created according to this example as a function of input. There is only one input in that example, X, as well as the states, okay? If you remember, we have to name these outputs because they have got all, both of them are Q. This can create a confusion. In order to avoid that confusion, we have to name them. So I'm going to name this as A and B so that I can differentiate these 2 states because they're not the same. They're outputs of 2 different flip-flops, okay? So therefore, I'm going to create the input for the next clock cycle. Okay, this is a rising edge, as you can see. It's a rising edge flip-flop. Therefore, in order to know what would the state be in the next rising edge, then you have to calculate this input, because this input would be your next state. Okay, according to the functionality input-output relationship of the D flip-flop, we know that input would be our next state. Okay, so therefore, this example assumes the following. You have A, we got the A, and we end this A with X. Okay, so therefore these are ended. All right, and we have got also X ended with B. This is your B, okay, and I'm going to draw B like this. All right, and this is your X again, maybe another AND gate. Okay, and this is your X again. All right, and these 2 will be ORed together. Okay, here we go. ORed together to generate this D. Okay, this is an example, by the way. So don't worry about where this is coming from. I just given to you. This is circuit analysis. Remember, we're not designing anything yet. This is just an example, okay? all we have to do is to analyze the circuit. What is this circuit is doing? Okay, that's the basic question here. Okay, analysis of the circuit. How about the second input? The second input is A prime T, which is this, right? Okay, A prime T and X, again, and here is an X. If you AND them together, you figure out the next state of this flip-flop, okay? Okay, that's it. That is actually telling us what the next state B would be, okay, of these two flip-flops based on input and the previous states, A and B, okay? This is exactly how the circuit will generate the next state. But we don't always have such a circuit. We sometimes have an output. Because if there is no output, unless you use these outputs as your circuit output, because this could be also the case. For example, this could be, these two could be the output as well, okay, of the circuit. But we can have extra outputs, which can be a function of the states as well as the input, okay, the same way. So therefore, I'm going to also define an output, which is Y, let's say. So let me erase this part here. All right, so output is given by BT, so that is part of the output, BT, and AT, right? So maybe I can use this. These two are OR together in my output, and I have X prime T, right? This is my prime. This is ANDed with the X prime, you got Y, okay? That is your output. You can define alternative outputs, by the way. You can define as many outputs as you like, okay? It doesn't, I mean, the number of outputs is not a big deal. You can have any number of outputs you like. The important thing is that what is the relationship of this output, input, and the states, okay? Again, this was one of the basic examples we were given in our online meeting, if you recall. Okay? Now I'm going through it. So the first thing we in the analysis, what we're doing in the first place is to write down the state equations. Okay? State equations meaning that what it would be the states in the next rising edge. So let me draw the clock for you. Okay, so this is clock, right? So let me just draw the clock for you. This is my clock signal. It's a square, periodic square wave. Okay, I couldn't draw it into scale, unfortunately. But treat this as a, periodic square wave where periods are the same. So this is actually same as this one, same as this one, same as this one, okay? And this circuit is a rising edge circuit, right? These flip-flops change state in the rising edges. In other words, this is where the state could change, and this is where this state can change, and can change here, and change here, okay? What happens to the rest of the time? It holds it. It holds the value. Whatever it's storing, it's going to store, okay, for as long as this period. And then it looks at the input, and then whatever it sees as the input, it changes state to that input, and then stays there for that period of time, okay? That's how these two circuits behave, all right? All right, so remembering this, I would like to calculate what would happen in the next clock cycle, okay? With that clock cycle at that particular point, okay? The input is already calculated because it's a combinational circuit that gets the value from the previous round, okay? Here, it gets the previous round because this is the previous state. At that particular moment, I'm going to call this period of time as AT, this period of time as AT plus 1, and this period of time AT plus 2, meaning that the output of this flip-flop, okay? Because it's not going to change, right? During this time, the output will always be always the same. And this is your AT plus 1, this is your AT. What I would like to do is, I would like to calculate AT plus 1, the next state value, in terms of the previous state, and the input, of course, right? So that is the state equation, actually. Because if you define AT plus 1 in terms of AT and XT, the input, okay, then you can define AT plus 2 in terms of AT plus 1 and XT plus 1, okay? So defining the relationship by only looking at these two periods would be more than sufficient. It's going to define everything for you. Okay, you can apply the same functionality to the next two, and then the next two, and then the next two. Okay, so let me write it down. AT plus 1 is the next state of this flip-flop. This is your AT, okay, previous state. AT and XT gets ended together. Okay, so this is AT, XT. Ended together. And I have got XT, what is that? This is BT. So I got BT, XT, and then these are OR together. You see and then OR. So that's why I have got plus sign. All right? So this is my next, the state equation for this flip-flop because it defines the next state of the flip-flop. Okay? Similarly, we have defined the next state of this flip-flop, which I'm going to call BT plus 1, as A prime T and XT. And finally, we have YT. Remember that YT is not a YT plus 1, because whenever you're in this period, YT is automatically calculated based on the states, AT and BT, as well as XT. Okay, it doesn't have to wait for the next state to come, because it's a combinational circuit, remember? Okay? All right, and YT is equals to AT plus BT and X prime T. Okay? Again, this is X prime T, this is AT plus BT, and you end them together. Okay, that's exactly what this combinational circuit tells me to do, and that's why I wrote the Boolean expression just like this. Okay? All right, so these equations are all the state equations you need, okay, to describe what's happening in this circuit. All right? So let me also give you a detail here. So for instance, let's suppose that AT is 0, right? So let's just equals AT equals 0. So that means I am in this particular period, okay? In this particular period. Whenever you have a rising edge, AT is determined right in this particular time instant. Okay? In that particular time instant, AT is determined. So let's suppose it's AT equals 0. And BT, let's suppose BT equals, at that particular moment, let's say it's B1. Okay? You know, whenever this becomes 0 and this becomes 1, then these are going to propagate through these circuits. You see these are 1s, and let's suppose XT is also 1. These are going to, particularly AT and BT, they're going to be propagated through these wires, okay? Making this 1 and this one as, sorry, this is 0, right? Because this is 0. This is 1, and you got a 1. So this 1 will appear at the input of the circuit almost instantly. Because it's combinational circuit, remember. This period is chosen such that it's way bigger than this gate delays here. Okay, so it actually automatically creates a value here. That would be your next state. However, you have to wait for the next clock cycle to assume this to be your next state. In other words, this one here is determined right here. Okay? A minuscule of time. And then you wait until you hit the next rising edge so that you can assume that value to be your next state. In other words, you get this one inside of the circuit, so that's going to be stored now. Okay? And some people ask me, how is this period is determined? Well, that period is usually determined based on your combinational circuit delay, right? If your period is smaller than this small delay that I've drawn here, if this small delay is bigger than the period, then the value 1 couldn't be determined before you take this value inside the flip-flop. And that would create a confusion, right? And your circuit will not allow to work properly. So the thing is that people, make these periods smaller and smaller, because smaller period means faster circuit, right? Smaller and smaller until they become so close to that delay, this gate delay here, okay? That they could not do more they could not shrink the period more because that would create a problem in terms of the delay these gates create. Okay?
I couldn't understand how we obtained A prime T x T for B T prime.
This one? Okay.
Doesn't it x B?
So you see this is A prime, right? So this is A prime T coming in. Okay. And this one is xt. So therefore this is A prime T xt, which is going to be your next state in the next rising edge. Okay? Did you get it now?
Mm-hmm.
Okay. Again, one of the challenges of sequential circuit is compared to combinational circuit, that there is a time component here. Okay? That's the only difference actually. The rest is just the input-output relationship. Okay? You got now states as your inputs, like the previous state, as your input, and next state would be your output. And if you got extra outputs like Y, that would also be your output. Okay? But that's the only difference, the time component. Okay, because which creates a memory inside your system. Okay. Since it came true now to my attention, I'd like to just jump to an important, because this is an example, right? This is an example, and if you look at this example, one of the things that you realize that these are states, these are the ones that create states that I actually drawn in earlier. This is your state, right? This is the circuit that's state. I'm going to call it state elements maybe, right? No, state register. Just call it state register. Register means a data memory element that can store only one bit, okay? A register, a simple register. Of course, that you can store multiple bits if you like. That would also be called register, okay? But the minimum amount of information you can store in a register is just a single bit. So register actually is equivalent to one of the flip-flops. It could be a JK flip-flop, D flip-flop, or T flip-flop. It doesn't matter. You store one bit, you can treat it as a register. And we shall see later on, multiple flip-flops stacked together will create a big register for you. Okay? And I'm not sure if you have seen or heard concept of register before. Have you heard it before? Registers? No? That's the first time? Okay. Then anyway, forget it. So registers are actually the smaller memory components that can store one bit. Okay? At least one bit. So these are state registers actually because they store 2 bits. You can see 2 bits. They could be 00, 01, 10, and 11. Each one of them corresponds to a specific state. All right. What you're seeing actually in front, right here, let me draw with using another color. This one. So this one, for instance, including, this is not included, sorry. Including this AND gate here, okay? This is called front-end combinational circuit. Okay? Front-end combinational circuit. Why did I say front-end? Because we may have a back-end combinational circuit, which is this one. Okay? The back-end combinational circuit is a function of state registers, and sometimes input as well. Okay? So this is your back-end combinational circuit. Okay? Now, if you look at the output is a function of states as well as the input. Okay? Right? So, if you would like to draw this circuit once again with this blocks only, without considering this specific example, I'm going to just draw the following diagram for you. There are 3 blocks. Okay? In general, you will be faced with 3 blocks. The first block is front-end combinational circuit. The second is state register. And third one is back-end combinational circuit. Okay? So the relationship between these blocks, you basically use front-end to provide the state information. In other words, inputs of these flip-flops come from the front end. As you can see, it's the case here, right? You see, this input becomes your next state, and this input becomes your next state, and these are coming from the front-end combinational circuit. Okay? And of course, state registers generates an output for the backend. For example, this backend. All right? And of course, state registers can be used by the front end, right, to generate the next state. In other words, these outputs here, these are fed back into the front-end combinational circuit, along with the input to generate the next state. Okay, so there's going to be input here, of course. All right? And this backend is a function of state register. For example, this Y is a function of state registers as well as the input, right? So input can also play out some role for the backend. Okay? So in this example, you see every single one of these happening. But it doesn't have to be that way. In other words, sometimes your backend may not use the input at all. But in this example, it uses the input as well, right? Because Y is a function of states, these A, B, and T, AT and BT, but also is a function of input. What I'm saying is, sometimes it doesn't have to use input. In other words, you can just break this link. Okay? In another example. I'm not sure that JK flip-flop example is something like this. So let me just check. No, it also uses input as well. Okay. Anyway. So if the backend uses inputs as part of its calculation, in other words, if this link is here, exists, this is called Mealy circuit. They have got different names, by the way. Okay, so Mealy circuit. M-E-A, sorry about my writing, M-E-A-L-Y. Okay, Mealy circuit. And if this doesn't exist, of course, that becomes Moore circuit. So this feedback loop exists in both Mealy and Moore, all right? So Mealy plus Moore, Moore M-O-O-R-E, okay? But this link only exists in Mealy circuits, okay? In other words, if you see output being a function of not just the states, but also input, then you call this circuit as a Mealy circuit. So this is a Mealy circuit example, okay? It's a Mealy circuit. Okay? And if we didn't have this link here, right here, for example, if I break this, okay, then this would become only a function of inputs, of states, state is inputs, that would make this as Moore circuit. Okay? Okay, why did we learn about Moore and Mealy in the first place? Well, because there are differences between these two sequential circuits. In the Mealy circuit, for instance, Y is determined instantly if X changes, right? If X changes, Y changes at that particular instant. There is no flip-flop between these two, right? In the Moore circuit, for instance, since X is not part of the output, it's going to be only a function of the output of these flip-flops. That means Y can only change at the rising edges, right? So therefore, this is going to create more synchronicity in your circuit. This would be synchronous with the clock. However, if there's something wrong with X in the Mealy circuit, if X is not synchronous with the clock, that means Y will not be synchronous with your clock. Because at the particular instant that X changes somewhere in between, somewhere, for example, right here, for example, X changes. That means at that particular moment, Y changes. Because it's automatically propagated to the output. Okay? Because Y is a function of X. Okay? So it doesn't wait. Y does not wait for the next rising edge to change. It changes automatically as X changes. Okay? So that's, for example, one of the major differences between Mealy and Moore. Sometimes you want, synchronous circuits. And this is going to also create noise failure tolerance, for example. If there's a noise in the X, Noise, you don't get me wrong, in the X, when I say noise, it's not always the amplitude, it's sometimes the phase, you know. X can also confuse itself with the clock. So it can actually go a little ahead of the clock. Sometimes it can lag behind the clock. Okay, that's also a noise, okay, in time. So therefore, if there's a noise on X, that can be reflected upon Y automatically. In the, of course, Mealy circuit. In the Moore circuit, there is no such a problem. Even if X has got that problem in time, okay, shift problem, that would not be created in Y because Y is synchronous with clock. It can only change at this particular rising edges, okay? Okay, is that clear? I got the opportunity, of course, in a face-to-face meeting to go into the details, which I couldn't in our online meeting. All right, so that's good. But I'd like to go through that other example. So remember, once you had this, then the next step was to create the truth table from here, right? Truth table, just like we did for combinational circuits. Then from that truth table, you go to state table, and of course, state diagram, right? Diagram. And we created the state diagram, if you remember, right? So let me draw the state diagram right here, and then talk about, which we couldn't in our last meeting because of the time limitation. Let's talk about what this circuit is doing. Is it something useful, or is it something dumb? Okay? So let's just draw the state. So I'm skipping some of the steps which we have covered in our online meeting because I'd like to reserve some time for the next example. All right? So let me just directly draw the state diagram for you. Okay? Remember, we got two flip-flops. That means each one of them can have 0 and 1. So therefore, there are 4 combinations. Therefore, you got 4 states. Okay? That's why we have, I'm drawing 4 circles on the board. So we got 0, 0. We got 0, 1 here, 1, 0, 1, 1. I mean, you can do it any order, by the way. Okay? You can start with 0, 0 and write 0, 1 here. It doesn't matter. Okay? It will be the same. Okay, so whenever you have 0, 0 in your flip-flop and input is 0, you turn out to be staying in the same state, and your output would be 0. Sorry, not 1, 0. This is from the state table we drew last time. Okay, and whenever you have, again, in the same state, whenever you have an input of 1, then what happens? You go from 0, 0 to, you go to 0, 1, the state changes, but output also stays the same. In other words, output is 0. Now, when you're in 0, 1, by the way, since there is only one input, right, X, that means you can have only 2 outgoing arrows. One for X equals 0 and one for X equals 1. If you got 2 inputs, that means you would have 4 outgoing arrows. One for X0, X1, let's say. X0 equals 0, X0, X1 equals 0. The other outgoing arrow would be X0 equals 0, X1 equals 1. And the other outgoing arrow would be X0 equals 1, X1 equals 0. And finally, the final outgoing arrow would be X0 equals 1, X1 equals 1. Okay? Since you had 2 inputs. But in our example, we got only 1 input. So therefore, you got 2 outgoing arrows in each state. Okay? So in this case, you got this one and that one. In this case, for this state, you got 2 outgoing arrows. Which is, if you got 0, you got 0, output 1. And we got input 1, output 0. For 1, 1, we got 2 outgoing arrows again. For 1, you go to 1, 0. For 0, you go back to here, which is 0, 1. And finally, for this state, you got 2 outgoing arrows. One is X equals 1, Y equals 0. And finally, you go back here, X equals 1 and Y equals, X equals 0, Y equals 1. Okay? That's the state diagram. All right, now, final question for this particular analysis is that, what is this circuit doing? Okay? Maybe in the analysis part of the question, the most challenging, might be the most challenging with respect to the analysis of a sequential circuit. Because by just looking at this diagram, you have to turn this into something human readable, human understandable form. Okay? So my suggestion would be, give out a specific example and then see how the circuit will behave in that particular input. Okay? So I'm going to just write down the inputs, a specific input. Okay? Then we'll see what this circuit is doing. Maybe we can figure out something, maybe we couldn't. Okay, but we'll see. So let's suppose that I have got the following input: 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0. Okay? Let's see. If this is your input, in other words, this is your xt. Alright? If you know the finite state machine representation, this is also called finite state machine representation, or state diagram, I mean both works, you can actually generate the outputs if you know the inputs. Because this basically says that, let us start with state 0, 0. If input is 0, that basically tells you you have to stay in that state and push out a y equals 0. So let me use another color and show you what's happening. Okay, so what's happening here? So I'm actually in this state at t equals 0, let's say. So this is my t equals 0, okay? This is my t equals 1. This is t equals 2. T equals 3, blah, 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 blah. So at that particular moment, t equals 0, I have a 0 in the inputs, okay? That means, since this circuit says that if you have an input 0, push out a y 0 and you stay in the same state. So I'm going to push out a y, so that would generate a 0, output 0. But I have to keep the state, right? So I'm going to also have, this is yt, and this is state. Okay? Since I've got 2 bits for the state, I'm going to put 2 bits on top of each other, all right? To represent the state. And I'm going to do the following for you, just to create some space for each particular input. Okay? All right. So I'm going to draw this and draw that, and I'm going here. All right. Now, this generates a 0. What is the state? The next state? Next state would be 0, 0. So I'm going to stay here 0, 0. This is my next state. Okay. Okay, I see another 0 at the input. But if I see another 0 in the input, then I'm going to stay in the next state and then generate another y equals 0. So that would be 0 and 0, 0. And I've got 1. So as long as I see at the input 0, okay, then that means I'm going to stay in the input, in the initial state 0, 0, okay, all the time. So input has to be 1 in order to leave this state. Okay, I think you can clearly see that. So let's suppose that the first input, 1, comes in the third place, t equals 2 case. That would actually push me to move from this state to this state. And that would generate another 0. Okay? So that is 0 again. But I am in this different state now. 0, 1. Let's just say this is MSB. And this is LSB, all right? Just convention. Just a convention. So it's 0, 1. Okay, now then I see another 0, so that means I go back to where I start, because that is what this is saying. Okay, so therefore I'm going to go back to my initial state, but I push out a 1 here, you see? I push out a 1 here, so that actually creates a 1. Okay? Now you have to think about why this 1 has been created. Because of this one, right? Okay, let's keep that in mind and continue, see if that would change, this idea, this observation change as input moves through time. So we got now in the initial state now, and then I see another 1. So I see another 1, and then, so this one, and that would create to move, make me move from 0, 0 to 0, 1, and then I create another 0 outputs. And then I see another 1, which would put me from this state to this state, transition from this state to this state, okay? Which means I'm going to move to 1, 1, right? And I create y equals 0, okay? So y still is 0. And then I see another one, which would put me from this state to this state, transition from this state to this state, which means I'm going to have to move to this next state, and I create another 0. Okay? So I keep actually creating zeros, irrespective of the input, because the inputs are still ones, and not zeros, but it still creates, a 0. All right? And then finally I have a 0 here. Okay, I have a 0. So therefore, if I am here, and if I see a 0, I move to this initial state, right? So I'm going to actually create the 0, 0, and create a y equals 1. All right, perfect. Now things are getting clear, because this one now is created after seeing all these 3 ones, right? Not just a single one, because if this was the case, then I should have seen the 1 and 1 here, but they're all zeros. This one is created because of these 3 ones. Okay? All right, good. And then if I see this 1 again, this will transition from here to here, and then another 0, go back to here. So I'm actually now getting a bit speedier because we've covered that case. So that means 1 is going to put me to 0, 1 state and create a 0, and then that 0 will push me back to the initial state, which will 0, 0, but that will create a 1. Again, because of this one now. All right? And continuing that way, 1, 1 will push me here, and then 0, go back here, right? But that would create a 0, 0, 1. Okay? So this is 0, 0, 1, and this would push me 0, 1, and 1, 1, and then 0, 0. Okay? And it continues like that. So now, it's time to guess. What is this circuit doing? I've got 1 here, 1 here, 1 here, 1 here. So let me ask you another input, all right? So let me just ask you this. 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0. Okay. The output, because the logic is now simpler. Now we understand how to behave. So I would actually guess the following output for this input. I'm going to say this is 0. 0, 0, 0, 0, 0, 0, for as long as this one. And then next one, this should be 1. And then I'm going to have 0, 0, 0, 0, and then 1 because of these 2 ones, right? That should be the output because of the logic that we just presented here. Okay, so what does that mean? These ones are pushed out because of these groups of ones, right? There are piles, and there is a specific name for that, runs of ones. Okay? So there is a specific run of 1 here, right? And that one actually is generated because of those runs of ones. See that one? You see, you got a 1 here, 1 here, 1 here, and as long as you have got 1 in the input, you will stay in this state for as long as you see an input 1. Okay, and that generates always a 0. And finally, when you see a 0, input 0, you go back to this state, which is actually like, absorbing all consecutive ones until you see a 0, and then it pushes out a 1. So what is these ones then? Well, those ones actually tell you how many runs of ones you have in the input. For example, if you sum them, 1, 2, 3, 4, that actually says there are 4 runs of ones in the input. Okay, and it's kind of easy to calculate that for a number because you basically push the sequence to a serial adder, which we haven't covered yet, but there are serial adders. It does, long streams of 1s and 0s, it sums them and create those numbers, okay? So that means this circuit actually, if this is connected to a serial adder, that can actually tell us how many runs of 1s we have in an input sequence, okay? You may see that, well, this is a very simple logic. I mean, runs of 1s. I mean, who the hell would need runs of 1s in a digital circuit? Well, it's very, very critical, important information for digital circuits. Okay, runs of 1s are very, very important because if you got those runs of 1s, for example, bigger than 100 or 1,000, okay, That would be big problem for communication systems, because communication systems use these bits to synchronize. Okay, I'm trying to synchronize with you, and I'm sending all these zeros and ones, and it turns out that data has lots of runs on ones. So that means signal doesn't change. So you cannot identify whether the signal is not changing because you're not getting any signal, or somebody sending you one all the time. You don't know which one is true. Okay? That's why runs on ones is important. You don't allow, for example, runs on ones to go beyond 100 or 1,000. Okay? Because that can create a signal identification problem. Whether the receiver is getting some normal signal or just a stream of ones, because data is stream of ones. Okay? We don't know that. We cannot differentiate it. That's why runs on ones is very, very important. Okay. After having motivated ourselves with this simple example, okay? So you see now, you've seen all the stages of an analysis of a circuit. Okay? You've seen that you're given this circuit. You know, who, for example, in the class could tell me whether this circuit was doing this runs of ones problems, solving the runs of ones problem, or telling us how many runs of ones would appear in the inputs? Okay? No one. Okay? But after the analysis, we are able to say that. We are able to say this is counting the number of ones, or telling us where the runs of ones are, right, in time, through pushing one at the output. Okay. Any questions? Question?
By analysis, do you mean input this and then trying to input number one and see the Y output? Then is this the analysis process being?
Say again.
Is the analysis the thing that we did in the dashboard? So we can use if we knew the X in this circuit, and we could use the analysis again for this circuit again to see the Y, and we could see there are 1,000 ones and groups of ones or ones and ones. Right?
So you need an input, of course.
If you knew the input.
If we knew the input, we can tell where the runs of ones ends. This is what this output says. This output says that at this particular time instant, this input had got one runs of one. It doesn't tell you the run length, of course. It just says that there is a runs of ones. Maybe it's length 1, maybe it's length 3, maybe it's length 20. Okay? It says there's a run of 1 here. And then 0, 0, 0, and then you see one out the output. It says that another runs of ones I see. Okay? In this case, it's 3, length 3. And then you got see another one. You see, oh, there I have got another runs of ones. And then you got another one. For this particular example, you see all these zeros, right? And then you got a 1. So that says, oh, I have seen a runs of ones. Okay? And that's why I push out a 1. And then you got another, accumulation of zeros, and then extra 1 here, which says I've seen another runs of ones. Okay? But it doesn't tell you the length of the runs of ones. Okay? You have to design another circuit for that particular purpose. Okay? But this circuit just says I've identified a runs of ones. Okay?
If we had 1,000 runs of ones.
Yes?
Would it be just 1,000 ones in the input? Because we would create the same thing.
Input can have 1,000 consecutive ones in 1,000 places. Okay, digits actually. So therefore, it is possible, and this circuit will only output single one at the end of that 1,000 ones.
So how would you know if we need to make an error out of this?
Error?
Yeah.
What type of error?
Yeah, if we have 1,000 runs of ones, how do we know if we have 10,000 ones in the input or not? If we could have, how do we determine that this could be a communication error during the communication? So
During the communication?
You said if we have 1,000 runs of ones, we could have the same input over and over, or somebody could be sending us the ones over and over again.
Okay, so let me rephrase my example in terms of communication systems. In communication systems, we send data, right? So I send you data, and I send you an image, for instance, a black image, a big black image. Okay, there is nothing in the image. I just happen to send that to you, okay, erroneously, and because it's black, it sends all ones to you. Okay, it's just digits are all ones because it's a black screen. So therefore, I send you all the time 1, 1, 1, 1, 1, 1, maybe million of times. So at the receiver, you're getting those ones, but at some point, the communication systems use those bits to synchronize itself with the transmitter. Since there is no zero, that synchronization information, because of the jitter, delay, and other things, environmental conditions, etc., that jitter would be accumulated because there is no zero, right? So at some point, receiver will think that the signal may not be coming to me because what I'm seeing is just ones. In other words, 5 volts all the time. Signal is just fixed. So you cannot differentiate whether it's a data or because of some problem in the communication channel, it happens to have, it just happens that I'm receiving all the time 1 because of an error in the communication channel. That cannot be differentiated if you send ones all the time. Okay? That's the problem. So if you, for example, in the transmitter, limit the number of runs to some number, for example, 1,000, then that problem would not happen. Because 1,000 is something that is tolerable from a receiver point of view.
So we limit the not to ones.
Yeah, we limit it.
So we
Yes.
limit the ones on ones?
Yes, we limit the rounds of ones. We limit the rounds of ones, for instance. In magnetic storage devices, for example, rounds of ones and rounds of zeros are limited because of this particular problem, synchronization problem. Okay? And there are different codes for that. We don't send this data as is. We basically go through some kind of transformation, some coding, so that we got these constraints on the bit streams, such as rounds of ones cannot be greater than 7, and rounds of zeros cannot be greater than 0 and smaller than, for example, 2. Those type of constraints can be imposed on the data so that you can have these communication and data storage devices work properly. Is that clear? Okay, any more questions?
Can I ask?
Yep.
I didn't understand the procedure of the calculating the output depending on the state.
Calculating output,
Depending on the each state.
X state, which is input.
Yes.
Yeah, so you look at this, you see Y, its output is a function of these two, which are, if you just follow through these wires, one of them goes to A prime T, and the other goes to A T. Sorry, maybe it's not going A prime T, sorry, this might be, is it A prime T? Oops, I think I've done something wrong here, because, this has to be B, right?
B and A.
DNA. So I think this is wrong, right? This has to be here, right? Because this has to be B. This is B, you see B, this is A. So this is A plus B, okay? And you have X coming in, X prime. So you got A plus B, X prime T. So Y is a function of inputs, XT. So whenever XT changes, Y changes. Okay? It's a function of X also, not just the states. But as I said, this is a Mealy circuit. That's why we have this relationship. In the Moore equivalent, we don't have that link here. Therefore, output would not be a function of input. It would be only a function of state registers. In other words, states. Okay? All right, so we got this class exercise, which I'm going to go through a little faster than this example, because I think I've gone through the details well with this example. But one of the things that is different in this example is that we have a JK flip-flop. So I'm going to have to teach you how you deal with a different flip-flop rather than a D flip-flop. D flip-flop is kind of the input and output relationship is easy, right? Because input is going to be your next state. It's pretty easy. However, in JK flip-flops, remember, input-output relationship is not that straightforward. It has a certain relationship. And of course, JK flip-flops have got 2 inputs rather than 1 input. So let me draw the circuit diagram for you. So I got 2 JK flip-flops. I have got JK and a clock, and JK and a clock. Okay. Now, I'm going to, of course, name them. So this is my A, in other words, Q. And this is Q prime, A prime. And this is B, Q, Q prime, B prime, B prime. Okay, now this B is connected to the J input. Okay? And this Q prime or B prime is connected to K in this example. Similarly, we have X, T as an input, goes into an OR gate with this
XOR.
output. Is it XOR?
I saw it as XOR.
No, there is an XOR for the output, but according to my example, this is OR gate. I mean, it doesn't matter, but XOR or doesn't matter. We're just analyzing a circuit. You know, this circuit is given to you. So let's just say, oh, this is OR, and you have a NOT gate here and here. Okay, both of them, and we have finally Y. Y is connected to this and B, I assume B, to an XOR. This is YT. All right. I think that's it. Yeah, that's pretty much it. This is your JK flip-flop based sequential circuit. So first question, is it a Mealy circuit or a Moore circuit? Mealy-Moore. I definitely would ask this question in the exam, by the way. Who says Mealy? 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 Moore? Who says it's Moore? There's only one person? Okay. Answer is Mealy. Because as I said, remember the definition. Output, if output is a function of input, it's a Mealy circuit. So that's that simple. You see the output, is this output a function of an input? Let's see. This goes through and then, yes. Because it's connected to inputs, right? So therefore, it has to change. If input changes and it's instantly reflected upon the output, then it's a Mealy circuit. Okay?
Teacher.
Anyway, question?
It was XOR.
At XOR? Okay. So let's just change to XOR. As I said, it doesn't change anything. It's going to change the analysis, of course. But from an example point of view, right, for you students, it doesn't really change anything. Okay, so let's just look at this example. So what do we do with this? As I said before, we need to calculate the state equations. Yeah, that's the first we do. First thing we do. So how many equations we're talking about? I need a state equation for this flip-flop, A, for this flip-flop, and outputs. 3 state equations. Okay? So let's just write it down. What is AT plus 1? Okay, that's the question. You know, was in the next clock cycle, when you see an NXI rising edge, what would be the next state of this JK flip-flop? That's the question. Okay? Can anybody tell me what AT plus 1 would be?
Yes. It's BT A prime T.
BT A prime T, yes?
Or B prime T prime A T.
B prime? Say again, B prime?
The prime of that. So it's BT actually.
Okay, BT, okay.
And AT.
AT.
That's what I thought.
Okay. And your name?
Kerem.
Kerem. Kerem says, I believe this AT plus 1, in other words, the next state of this JK flip-flop on the left, is a function of the states, and this is the Boolean expression that corresponds to that states. Okay? All right, so in order to verify Kerem's, and anybody who have got a different answer? Anybody who suggests otherwise? Or anybody who suggests anything? Or anybody who agrees with that? You agree? Perfect. Anybody else? No? All right, let's verify that. So this is BT, right? So this BT comes in. So that's actually very, very nice because I actually find a lot of resemblance between analysis and that toys babies are playing with. because you have to follow the wires. You know, remember those mazes? When we were a kid, we played those mazes, you know, to figure out a way out from the maze. That's exactly that. Sometimes, this is of course easy, but for more complicated circuits, it's just like maze. You have to follow the wires to get it out. So this is BT coming in here, and this is what? B prime T. Okay, now, all you have to remember, the functional relationship between J and K and the output Q. Remember that? What is that? Can you tell me? From your notes. What's the relationship between inputs and the output of a JK flip-flop? Say?
JQ prime
JQ prime
or K prime.
K prime Q
QT.
is your Q T plus 1, right?
Yes.
Or sometimes, I sometimes use, since I didn't put T's here, sometimes I use Q plus. And some literature does that as well. To indicate the next state, okay? So Q plus equals, that basically is actually T plus 1, okay? Sometimes people don't put T's because it complicates everything, right? That's why people use Q plus equals JQ prime plus K prime Q. That's the relationship. You don't need to memorize, by the way. You always have cheat sheets, right? So another reason to keep a cheat sheet. So you can write this down on your cheat sheet, and whenever it comes the time in the exam, okay, you use it from your cheat sheet. What's your performance of using the cheat sheet in the exam?
Zero.
What percentage of your cheat sheets you used?
5%.
Anybody who uses above 0? Like 10%? 5%? 5%?
5%.
Okay, good. It's a good score, actually. It's a good score. Okay. So, but this, you know, I don't even remember, by the way. This equation, I never remember. I don't memorize anything. Because I can always look it up. I don't need to memorize that. And you can also do the same thing through your cheat sheets. Just look at the cheat sheet. Don't worry about it. So, thanks to Kerem, who reminded me what that equation was. So I can use it, okay, to be able to calculate the next state. What is that state? AT plus 1. So this actually says AT plus 1 equals J. What is J? BT. So let's just write it down. AT plus 1 equals J, which is BT. I'm actually replacing everything, okay? I'm not doing anything magical. So this is J. J is BT. Okay? Q prime. What is Q prime?
A prime.
AT prime, right? So I use T, so I'm going to use A prime T. Okay? A prime T. Because it's Q prime, right? Q prime means A. Okay? Plus K prime. What is K?
B prime.
B prime. But prime prime gives you BT. So I'm going to write BT. And finally I have Q, but I know what Q is. A, AT. And looking back in here, Kerem was right. This is exactly what we're looking for. This is the relationship between output and JK flip-flop inputs. Can you tell me, again, through the same logic, through the same rationale, the output of the second flip-flop? In other words, what is BT plus 1?
It's a little bit more.
Now I expect everyone to, tell me the answer. Okay?
This is too long to say.
Is it harder?
Not too long to say.
Too long to say. Why is that?
I can try it.
Yep, of course, sure.
So we take the prime of AT XOR XT.
But let's do it together. Okay. Because I know that the rest of the guys would be maybe shocked to see such a big expression. Let's just derive it together so everybody can follow. All right, so here I see this is your input. So when I see it, this is AT and this is XT. So this is AT XT, right? And this comes in here and gets complemented, and it basically pushed into these J and K. But remember, when you have J and K connected to each other, what happens? In other words, they become the same. In other words, if I actually say, let's just use another letter, Z for instance, they become Z. Z Q prime plus Z prime Q. What is this?
XOR.
Z XOR Q. Okay. Right? Is that correct?
Yes.
Everybody agrees with that? Correct. So, So that means whatever I see here, which is the prime of this, is going to be, is my z, right? It's going to be my z, which is bt, right? bt is my q in this example. So therefore, I'm going to just write down at xt prime, right? Prime, and I have an XOR with bt, correct? Because that's what this is, z XOR q.
Why is no XOR in ANX?
Oh, this is XOR, right?
Yes.
Sorry about that, guys. Sorry about that. I'm getting old. That's a sign. I'm getting old. AT XOR XT, sorry. XT and prime. XOR BT. Oh, by the way, what is this? BT, right? We haven't done the simplification. But you can just take in the parentheses and see that it's BT. And you can actually show this, okay, to be AT XOR XT XOR BT and altogether primed. You can actually show that this is also true, if I'm not mistaken. But just go ahead and verify. I'm going to use, of course, this one because I don't know if that's true, but this needs to be true, I hope. Anyway, that's not the subject matter of this thing. So let's just also write YT. What is YT? YT is AT XOR, there's an XOR here, AT XOR BT XOR 80, right? So this is AT XOR BT XOR XT. Okay? All right. That's pretty much it. We have now this as a state equation for outputs. This BT is the state equation for the first flip-flop, and this is the second flip-flop state equation. Okay? How many minutes do I have? 12 minutes, okay, good. So next thing is to write down the state table. State table. So let's see if I can write it on the left-hand side. Just do it quickly. Here. Okay, let's see. I have got AT, BT, and XT, right? So I've got AT, BT, XT. All right? And I need AT plus 1, BT plus 1, and YT as my output. This is your state table, so to speak, truth table. I have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now, AT plus 1 is what? BT, right? So it's actually a copy of this column. You got 0, 0, 1, 1, 0, 0, 1, 1. What is the BT plus 1? It's the XOR of AT and XT prime and XOR BT. We got AT and XT, XOR them, which is 0. And then take the complement, 1. And that 1 is XORed with
1.
BT, so you got 1. Okay? And again, let's just do the same thing. XOR them, 1, complement 0, XOR 0. XOR them, 0, complement 1, XOR with that, 0. We got 0, 1, XOR 1, complement 0, 0, XOR with 1, 1. How about 1, 0, XOR 1, complement 0, 0 XOR 0, 0. 1, 1 XOR 0, complement 1, 1 XOR 0, I'm sorry, 1. And finally, we got 1, 0, XOR 1, complement 0, 0 XOR 1, 1. Finally, 1, 1, XOR 0, complement 1, 1 XOR 1, 0.
Wow. Teacher, is 80 is equal to complement of BT plus 1?
80 plus 1. Do you mean 80 plus 1?
Yeah.
80 plus 1 is BT.
No, BT plus 1.
BT plus 1, 80 XOR XT prime XOR BT.
Isn't it equal to EAT? EAT's complement?
Yeah, so that's what I said. It's actually YT's complement. So you can see that, right? Look at this, BT plus 1. If you XOR them, 0, 0, 0, you got 0. Complement is 1. 0, 0, 1, XOR makes it 1. Complement is 0. You got 0, 1, 0, XOR 1, complement 0. 0, 1, 1, XOR 0, complement 1. 1, 0, 0, XOR 1, complement 0. 1, 0, 1, XOR 0, complement 1. 1, 1, 0, XOR 0, complement 1. 1, 1, 1, XOR them together, you got 1, complement is 0. That's why I said, by heart. This has to be the case, okay? So therefore, this is actually what? YT prime, right? Because this is YT, this is YT prime. Okay? So therefore, this is going to be the prime of BT plus 1, 0, 1, 1, 0, 1, 0, 0, 1. Okay. So now we got everything in place. State diagram can be drawn now based on the state table. This is a state table. Okay? And by the way, we've got a lot of common terms here, right? A lot of common terms. For instance, this is just BT. This is YT prime. This is YT prime. Or you can write this as BT plus 1 prime. Right? These are all okay. Because this turns out to be a nice common term. Okay, now finally, I'd like to draw the state diagram here and see if we're doing something useful, and then I'll finish today's session. Okay? Okay, now, how many states do I have?
3. 3?
4. Because we got these 2 states. Each one of them could be 0, 0, 0, 1, 1, 0, 1, 1. Okay, if you got 2 flip-flops, please think about 2 to the number of flip-flops to be your number of states. You've got 0, 0, 0, 1, 1, 0, 1, 1. Now, by looking at this table, you can fill up the state diagram directly because there's a one-to-one relationship. You see 0, 0 becomes 0, 1. When input is 0, output is 0. So therefore, you go from 0 to 0, 1, input is 0, output is 0. Okay, that's my first row. Okay? Now the second row, 0, 0 goes to 0, 0, input is 1, output is 1. 0, 0 goes to 0, 0, input is 1, and output is 1. You got 0, 1 going to 1, 0. 0, 1 going to 1, 0. Input is 0, output is 1. You got 0, 1 going to 1, 1. Input is 1, output is 0. You got 1, 0 going to 0, 0. Input is 0, output is 1. And you got 1, 0 going to 0, 1. 1, 0 going to 0, 1. Input is 1, output is 0. And finally, 1, 1 goes to 1, 1. Input is 0, output is 0. And you got 1, 1 go to 1, 0. Input is 1, output is 1. Okay, I've actually gone through all these rows and then write it out here. Okay, when input is always 1, you always stay here and you generate a 1, apparently. But when you have a 0 in the input, and then another 0, for instance, and then another 0, you see, it generates a 0 here, and then 1, and then another 1. And if you got 0 and then 1, and then another 1, and then another 0, maybe the circuit is not doing something useful. I don't know. I mean, I have to look at it in more detail. Since we don't have time, let's just stop here.